So a rate law is a little statement that helps us understand the rate for a given reaction. So the first thing we want to understand is that every reaction has its own special rate law. Every reaction has its own special rate law. So here's a chemical reaction, A plus B reacting together to form something. Now, what's interesting about the rate law is the amount of material that exists in the product form doesn't change how fast the reaction proceeds. Okay? Why do you think that is? Whose turn is it? It's Alyssa's turn. Alyssa, why do you think that how fast the reaction proceeds doesn't depend on the product that's formed?
I mean, I feel like it depends more on the other factors, like the speed of the motion of like the molecules and the temperature, but I'm not really sure.
That's right. And what else? What was the one major thing that we said we were going to focus on in terms of the influencing the rate of the reaction?
The concentration.
The concentration. That's right. So because C, or the product, whatever it is now the product, it's not going to react with A or B. So because of that, it doesn't change how fast the reaction proceeds. It's just the product's parameters, like concentration of the product, or sorry, the reactants parameters, like the concentration of the reactants, the temperature of the reactants, the phases of the reactants, right? It's all about the reactants. Therefore, the rate law, the information about how fast a reaction occurs, doesn't talk about the concentration of the products at all, or doesn't even mention anything about the products. Okay? So, for a given chemical reaction, A going to be, I'll throw in the product just so it doesn't feel weird, just to say right product, I'll throw it in there. But for this chemical reaction, the generic rate law is written like this. The rate of the reaction, and we just write rate, meaning the rate of this reaction, will be equal to the concentration of A times the concentration of B raised to some parameters, right? We'll talk about those in a bit, times some constant, times a constant, which we call a rate constant, a rate constant. Now, for future use, I'd like to bring your attention to the shape of this K. It's shaped differently than other Ks. Some Ks look like this, whereas other Ks look like this. Jace, can you tell me the difference between those Ks?
Like represent different things?
They do, but what's the difference between these two Ks right here in terms of the way they look?
One's a lowercase, one's an uppercase on that. And then I know the big K stands for Kelvin.
No. That's the answer I wanted. One was a lowercase, and one is, I'm going to quote what you said. You said upper case. Do you know why we call them uppercase letters, Jace?
No.
Well, in the olden days, when people wanted to print something, they had a case of letters, 24 different slots, right? A, B, C, D, E, F, G, blah, 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 all the different letters. There's 24 or 26, I always forget. Whatever. They had some extras for periods, commas, semicolons, that's as well. They had a case full of all these letters, and they would take all the letters, and they'd line them up, and they'd put the paper on, and then roll the printer, the ink around to get a good printing. But then they had another case. They had the lower case, and then they had an upper case, which is exactly the same, but they were big letters. So that's where we got the term uppercase for. And I want to draw your attention to the fact that this is a lowercase k. And lowercase k's are what are used to represent rate constants. And that can be very effective and very important to understanding what people are talking about. When they use a lowercase k, they're referring to a rate constant. So, our rate law contains all of this. The word rate, a rate constant, the concentration of A, raised to a power times the concentration of B raised to a power. Those powers are what we call the rate order, the order of the reaction. We'll talk more about that, but just so we can reference it for now, it's called the order of a reaction. So, what this does for us is, like in this question, here's a chemical reaction, here's its rate law, right? So here's a question for you, Camille. Here's the chemical reaction, here's its rate law. If the concentration of A is 0.2 and the concentration of B is 0.3, what will the reaction's rate be? Well, what do these brackets mean here, Camille? The brackets are a way of expressing concentration. So when we see those brackets, we're saying the concentration of A. So the rate of this reaction here, this 2A to B plus B to equal 3C, the rate of the reaction can be determined by taking this rate constant, multiplying it by whatever the concentration of A is, and the concentration of B. All right? What's that?
Separately?
Well, no, together. So you take concentration of A, 0.2, times the concentration of B, 0.3, multiplying them together, and then multiplying that by 0.045. And that will be, okay, very good. So that tells us how fast this reaction up here, 2A plus B going to 3C, tells us how fast that reaction occurs. So the rate law is used for that information. The rate law, again, will tell you how fast this reaction will occur, and it will have to give you information about the K and the concentration and the relative orders for this reaction. We don't have it. Yeah, go ahead.
Sorry, so you said that in the original equation that they're raised to certain constant or certain numbers of x and y. Is that not applicable in this problem?
It is. It is. And apparently, what are A and B raised to?
1.
1. That's right. That's right. 1. And so what we could say is therefore, this reaction, we would say, is first order with respect to A and first order with respect to B, because these are raised to 1. Good.
Will they be given, or will we need to know how to find those?
Sometimes you are given information where you need to identify the order of the reaction with respect to a chemical. Sometimes you'll be given the rate law and you'll need to find the rate of the reaction. And in those cases, you'll need to be able to find the order of the reaction. And sometimes you want to know the rate of the reaction, but you don't have the rate law yet. And you have to find the rate law yourself. And after you find the rate law, you can use the concentrations with the rate law. So we got all sorts of possibilities, and we're going to learn all about it. Okay? So, how do you determine the rate law? I'm going to emphasize one more thing before we go on to that slide. Rate laws are specific to a given chemical reaction. So every chemical reaction gets its very own rate law. In fact, every chemical reaction at a specific temperature gets its own very own rate law. So if I have this chemical reaction here occurring at 20 degrees Celsius, it might have this rate law. But the rate law will change for a chemical reaction occurring at a different temperature, for example. Okay? So we have rate laws that are very specific to the given chemical reaction and the conditions. So, how do you determine a rate law? Experimentally. That's the answer. Rate laws are determined experimentally. So you have to do an experiment with the chemicals to find out what the rate law is for that given reaction. All right? So, let's take a look at some rate laws, some examples of some rate laws, and look at the reaction order for different chemicals in these rate laws. So I'm going to write a rate law here. Rate laws are always written like this. Rate equals lowercase k, concentrations of the reactants raised to different powers. And now if I ask Alyssa, what is the order of this reaction with respect to B? Alyssa will say,
A is the first order and B is the second.
that's right. So with respect to B, this is a second order reaction. With respect to A, this is a first order reaction. All right. If I have another rate law here for a different chemical reaction, I'm going to write a different rate law for a different chemical reaction. Rate equals lowercase k, A. All right. That's it. That's all. A. Right? Then this reaction is first order with respect to A. First order with respect to A. And apparently, whatever happens in this reaction, it's only dependent on the concentration of A to change the rate of the reaction. Whereas in this reaction here, the rate of the reaction is governed not just by the concentration of A, but it's also governed by the concentration of B. In fact, we can tell which one of these reactants, A or B, influences the rate of the reaction more. What do you think, Jace? Which one, A or B, will influence the rate of the reaction more?
B.
B will, because for every concentration change you get in B, we square that, right? Whereas the concentration of A influences, but it's not squared. So second order reaction means that this one influences the rate of the reaction more than the first order component does. All right. Now, units for A, in this case here. Again, those brackets mean molar, molar. So here I have molar. The rate of a reaction is always going to be expressed in terms of molar, which is molar per second, which is always, going to be the rate of the reaction. It's always the moles of material or moles per liter that are either removed or produced per second, right? And for rate laws, it's always the rate at which the material is disappearing because we're always talking about reactants. So the units for rate are always going to be molar per second. The concentration here of A, because it's to the 1, is going to be molar. And so that tells me what units I must have for my rate law here. Okay? Camille, can you see it? If this is units of molar and the rate is in units of molar per second, what are the units for my rate constant here, Camille? It's not just seconds, but it's what? It's 1 over seconds, right?
Oh, okay.
Can you see that? Because molar
Yes.
times 1 over
Molar
second
over second.
will give us mole per second. Very good. Now that is for one chemical reaction, but this rate law for a different chemical reaction, right? In this rate law, different chemical reaction, you have A, which is units in molar, and you have B, which is units in molar also, but these molar, this molar is squared, right? And then we have K, lowercase k, and that has to equal a rate. Now, whose turn is it? Sarah. What did I say the units for rate for a chemical reaction would always be?
Molar per second.
That's right. Molar per second. So, if this has to be molar per second, this is molar squared, what are my units for K then?
Okay, so it would be 1 over second per mole. Per mole, maybe.
Per 1 mole, here we have 1 molar and then we have 2, so a total of molar cubed, right?
Right.
So how many molars do we have to get rid of?
I have to get rid of
2,
2.
that's right. So for this one, it's 1 over molar squared seconds, or seconds molar squared. Can you see that? The K value there for this reaction, or the units for the K, change, again, based on the reactants and the order of the reactants. And what do you do if you want to get rid of some molars, Sarah?
If
What?
you want to get rid of some molars, you
Yes.
just multiply.
No, you go
This-
to the dentist, right? That's where you get
Oh.
rid of your molars, right?
Right, of course.
No, you're right, right. You just have the molars down below to get rid of enough so that you end up with just 1 molar per second, right? All right, very good. That was just a good joke that I always can't wait. Every year I get to share that joke. Okay, so how do we use information about a chemical reaction like this to determine what the rate law is? Okay. Well, here's what we have to do. First, we identify the rate of a reaction. Okay, so here's experiment 1, experiment 2, and experiment 3. These 3 experiments, I have concentrations of my different reactants. So here's NO. Here's my other reactant, O2. I react them together, and then I look at the rate at which the product appears. All right? So there's one experiment. Now, in my next experiment, Alyssa, I do the exact same thing, but I change one factor. Which factor have I changed, Alyssa, here in this second experiment?
The concentration of the NO?
The concentration of the NO. I doubled it, didn't I? Can you see that?
Yes, sir.
I doubled the concentration of the NO. And how did that change the rate of the reaction? Did it double the rate of the reaction?
Yes.
Are you sure?
I guess it like over doubled it.
It over doubled it. What did it do to it? Well, we can determine that by taking our 0.192 divided by what our initial reaction was, 0.048. True?
Yes.
So it quadrupled the rate, right? So we doubled the rate of doubled the concentration of NO, and we increased the rate 4 times. All right? So, help me out a little bit more, Alyssa. What do we know so far about what the rate law for this reaction is going to look like? Have the rate law for this reaction, what is it going to look like? What should I write down?
Well, we know that the rate is going to be molar over second.
Rate, that's right. The rate is going to be in units of molar per second. Rate equals, what else do I write?
The lowercase k.
Lowercase k, some constant, times what?
The concentration of NO.
Constant.
The concentration of O2.
Very good. Times, that's not plus, but times the concentration of O2. Very good. And NO is going to be raised to some value, and O2 is going to be raised to some value. Right? And what we've learned by looking at and comparing those first two reactions, what we learned is that if you take, let's say, X, concentration of NO, and Y, concentration of O2, and little k, the rate, let's say, would be 1. Is that okay? That's what maybe we see in experiment 1. And experiment 2, same little k. We haven't changed the temperature. We've just changed the concentrations. But X is different now in reaction 2. We've used twice as much X. Right? We used twice as much X. And how did we change the concentration of O2, Alyssa, for the second reaction?
It stayed the same.
It stayed the same. So, how did the rate change over here? It's quadrupled, so we can put a 4 there. Now, from these two equations, we can find out what this X is. Because these two things didn't change. They were the same. These two things didn't change either. They were the same. All we did is we doubled this. So we went from 1 to 2, and this went from 1 to 4. So what does that mean, Alyssa? What must the X be? 2. It has to be a 2. Very good. So we learn more about our rate law. Our rate law is now rate equals K times the concentration of NO, but we know that this is raised to the 2, second power. All right, so we're learning more about our rate law. We don't know what the value is up here yet, right? But we can learn. We can learn. Let's find 2 reactions that will allow us to learn about that, Jace. Which 2 can we look at? Which 2 will tell us the influence of the concentration of oxygen gas on the rate of the reaction?
We're going to be looking at the NO. If we're looking for oxygen, we're going to want to look at the NO and the NO2.
All right.
Right?
Well, we want to compare experiment 1 here with experiment 3. Because in that experiment, we don't change the concentration of NO. We only change the concentration of O2.
Okay.
And
Yeah,
when we do that, how does the rate of the reaction change?
It gets smaller.
Well, it goes from 0.048 molar per second to now 0.096 molar per second.
Oh yeah, never mind, it doubles.
It doubles. 0.096 divided by 0.048. That's 2. All right, so what we've learned is set up another box like this one here, but for oxygen. If we take some X, we know it's raised to the 2, and we use the same X in both reactions. This is experiment 1 and experiment 3. What we changed was our concentration of oxygen gas, right? We doubled the concentration of oxygen gas from experiment 1. We doubled it.
Sorry, I thought I did.
And the rate here How does the rate change, Camille? From experiment 1 to experiment 3? It's too small to see.
It gets smaller.
Let's see. Here we go. Let's look. Rate
Thank you.
experiment 1 to experiment
So
3.
it gets higher.
It not just gets higher, it doubles, right? It doubles.
It's up.
Doubles. So from 1 to 3, the rate went from, we can choose whatever value we want. Say it doubled. And so what does that tell us about the exponent on y then, Camille? There's a lowercase k, but none of these things changed in our 2 experiments. The only thing we changed was the concentration of y. So what does that tell us, Camille? What is
the exponent even change?
the exponent?
When
What?
it doubles?
It didn't. Well, we used a concentration.
The exponent wouldn't change, would it?
It doesn't. Well, no, the exponent doesn't change for sure. But can we identify what the number is here? Can we tell what the number is here?
1.
It's 1. It's 1. Very good. And the way we knew that is by doubling this, all we did was double the rate. So this must be equal to 1. So there it is. There is our rate law up to this point, right? If you have to get going, you have to get going, and you're welcome to leave. This isn't a good place to end the class, and so I'm going to show a few more things to find K so that we can give one complete example of how to do this. But I understand if you have to get going. But all we do now is once we have this rate law, rate equals little k times the concentration of NO squared times the concentration of oxygen. All we do is we choose any experiment, experiment 1, experiment 2, experiment 3, any one, and choose the concentrations of the reactants and put them into this reaction, and choose the rate of the reaction and put it in over here, and we can solve for our lowercase k. So this is the rate law that we've learned so far. I'll choose the first experiment, 0.015 squared, 0.015. This is again choosing experiment 1 here to the 1. Lowercase k is what we're trying to solve for, and the result for this reaction was 0.048 molar per second. I can use my calculator here and take 0.048 and divide it by 0.015 and do that 2 more times, and that's 14,200. That should be our K value. 14 times 10 to the, or 1.4 times 10 to the 4th. 1.4 times 10 to the 4th. So then what we have here is the finished rate law, which is rate 1.4 times 10 to the 4th, times 10 to the 4th, concentration of NO squared, concentration of O2 to the 1, right? And now I just have to make sure I get the correct units. The rate is going to be in molar per second. So this is going to be in something per second. I have 1, 2, 3 molars up here. 1 over, I want 3. I have 3 molars. I only want 1 molar. So I'm going to put molar squared down there. So that is my final rate law then. Okay, very good. All right, well, thank you guys for sticking